Join me as we delve into the mysteries of the universe's boundaries, exploring what lies beyond the observable and whether it truly exists. Have you ever gazed up at the night sky and wondered what lies beyond the stars? Our universe is vast, but not even the most powerful telescopes can see beyond it. What lies beyond the observable, then, is the part of the universe that we can observe and study, which encompasses all the universe as it is right now, including all the stars, galaxies, planets, and other objects visible to the naked eye, is constrained by the distance that light has traveled since the Big Bang, which scientists believe to have occurred around 138 billion years ago. Since light has a finite speed, we can only perceive objects whose light has had ample time to reach us since the Big Bang. Range, anything beyond which our light has not yet reached, renders it invisible. The observable universe is vast, with an estimated diameter of 93 billion light-years. As a result, the furthest objects visible to the human eye are 465 billion light-years away in all directions. The reason this figure exceeds the age of the universe in light-years is due to the fact that the universe has been expanding since the Big Bang, stretching the boundaries of our observable universe. Light travels at a speed of approximately 300,000 kilometers per second, or 186,000 meters per second. Since the universe is 138 billion years old, the furthest light we can see has been traveling for 138 billion years. However, due to the expansion of the universe, the objects that emitted this light are now significantly farther away than 138 billion light-years. This edge beyond the visible universe is known as the cosmic horizon, and no amount of technological advancement in telescopes can bring it into view. We have come a long way, baby, in our knowledge of space and its inhabitants. Long ago, when people looked up at the sky, they saw planets and stars, but they had no notion how far away they were. Instead, they thought the stars were stationary points on a celestial sphere that encircled the Earth. Different cultures had different views on the universe, and each culture's cosmology reflected its knowledge and beliefs. For instance, the ancient Egyptians believed that the sun and moon were. In ancient Mesopotamia, the sun god Ra was believed to sail across the sky during the day and bring light and life to the world from the underworld at night. The sky was seen as a dome with stars embedded in it, and the Babylonians believed it separated the heavens from the earth. Nut, the goddess arching over the earth, was believed to be married to Gbb. The stars were believed to be jewels on Nut's body. The ancient Greeks had a knack for astronomy and meticulously recorded celestial movements. They put this knowledge to use by making calendars and ECP predictions. As their understanding of the cosmos grew, they came up with more elaborate models. One of the first Greek philosophers, Anaximander, put forth the idea that Earth was a cylinder floating in space. Later, Pythagoras and his followers put forth the idea that Earth was a sphere. Observations like the shape of the solar system provided support for this idea. During a lunar eclipse, Earth's shadow falls on the moon. This idea was popular in ancient Greek philosophy, where Plato held that the heavens were static and flawless, and that the planets and stars orbited the Earth in perfect circles. Aristotle, Plato's student, expanded on this idea and proposed a geocentric model of the universe, in which the Earth was at the center and everything else revolved around it. This view was widely accepted for centuries in China. Chinese astronomers meticulously recorded astronomical events, developed a lunar calendar, mapped the constellations and stars, and believed in a flat Earth covered by a hemispherical sky. During the Middle Ages, the geocentric model of the universe was dominant in Europe, mostly because of the influence of the Catholic Church. However, in the Islamic world, this view was challenged. Great strides were achieved in the field of astronomy thanks to the contributions of scholars like Ali, a Persian astronomer, and Nicholas Copernicus, a Polish astronomer who proposed a heliocentric model in which the Sun was at the center of the universe and Earth and other planets orbited it in the early 16th century. Although the geocentric model offered a simpler explanation for the observed motions of the planets, which appear to move in complex paths when viewed from a geocentric perspective, The revolutionary idea of a heliocentric model was not immediately accepted. Many people were reluctant to abandon the deeply ingrained geocentric model, but as time went on, more evidence supported the heliocentric model. In the early 17th century, Johannes Kepler utilized this model. Accurate observations allowed Kepler to formulate his laws of planetary motion, which depict the planet's orbits as ellipses instead of perfect circles. Galileo, an Italian astronomer, was instrumental in developing the heliocentric model through the use of a telescope. Galileo discovered several groundbreaking things like Jupiter's moons and Venus phases, which were in line with the Saronic system. Galileo's discoveries contradicted the conventional geocentric view and confronted. Despite facing opposition from the Catholic Church, his work laid the groundwork for modern astronomy. The next monumental shift in our knowledge of the cosmos occurred in the early 20th century with Albert Einstein's theories of relativity. Special relativity, which he introduced in 1905, radically altered our conceptions of space and time. According to this theory, the laws of physics apply to all observers, regardless of their relative motion. It also introduced the idea that the speed of light is constant. Einstein's general theory of relativity, published in 1915, further transformed our perception of gravity from a force between objects to an idea that energy could be transformed into matter and vice versa. Special relativity, which cannot be surpassed, was the driving force behind the famous equation EL-mc²2, which demonstrates that mass and energy are interchangeable. This had significant implications for our knowledge of the cosmos and the possibility of energy converting into matter. According to general relativity, the presence of massive objects, such as the sun, causes space-time to curve, which in turn affects the motion of smaller objects, like planets. This theory shed new light on the cosmos and predicted phenomena like gravitational lensing, the phenomenon where light is bent by gravity, and the existence of black holes, regions of space with so strong gravity that not even light can escape them. The predictions made by Einstein have been proven true by observations, which prove the theory's accuracy and power. His work also established the foundation for modern cosmology, which owes its understanding of the universe's dynamic expansion and contraction to the insights provided by astronomer Edwin Hubble in the 1920s. Hubble's discovery that distant galaxies are moving away from us lends credence to the Big Bang theory, which states that the universe started as a hot, dense point and has been expanding ever since. Edwin Hubble's revolutionary discovery in the 1920s about the expanding universe had a lasting impact on our understanding of the cosmos. Using powerful telescopes, Hubble measured the light from distant galaxies and found that it had redshifted, meaning it shifted towards the red end of the spectrum. This redshift indicated that the galaxies were receding from us, similar to how a siren's pitch lowers as it moves away. In the 1960s, additional evidence for the expanding universe came with the discovery that galaxies were moving away from each other, which led to the radical idea that the universe was static and unchanging. This expansion is often compared to a balloon being blown up, with galaxies like dots on the surface of the balloon moving apart as the balloon inflates. Meanwhile, observations led to the realization that the universe is expanding. The cosmic microwave background radiation is an important piece of evidence that supports the Big Bang theory. It is the leftover heat from the Big Bang that has cooled and been stretched to microwave wavelengths. It was accidentally discovered by scientists Arrow Pennis and Robert Wilson when they noticed a persistent noise in their radio antenna. The radiation is detectable in all directions. To the expansion of the cosmos, this radiation gives a picture of the cosmos at its most primordial state when atoms were born and the cosmos went transparent to light. By analyzing this radiation, scientists can piece together the universe's early conditions and its evolution over billions of years. The idea that the cosmos is expanding from a hot, dense core has prompted inquiries into the beginnings of this expansion, and to find answers to these questions, scientists have created. Theory of inflation postulates that, for a split second following the Big Bang, the cosmos went through a period of immensely fast expansion. During this brief interval, the cosmos grew exponentially from a small dot to a massive region. Inflation clarifies a number of crucial aspects of the cosmos, including the uniformity of the cosmic microwave background radiation, which would have been puzzling to explain without it. Is so consistent across the sky because faraway parts of the cosmos couldn't have possibly exchanged energy or information during inflation. This, in turn, explains the universe's large-scale structure and the theory's prediction that tiny quantum fluctuations during inflation led to the formation of galaxies and clusters of galaxies by stretching them to macroscopic scales and observing them as small temperature variations in them. The variations in cosmic microwave background radiation can teach us a lot about what happened during inflation and what the early universe was like. The theory of inflation and the expanding universe have huge implications for how we view the universe. According to these findings, the complex structures and galaxy arrays we observe today evolved from a simpler, more uniform state, all driven by physical laws. What will happen to the universe if its expansion keeps going? Will it eventually slow down and reverse, leading to a collapse? Current observations show that the expansion is actually speeding up, and scientists believe that this acceleration is caused by dark energy, a mysterious force that accounts for around 70% of the universe's total energy. Understanding the nature of dark energy, which is one of the biggest mysteries in cosmology, could shed light on the ultimate fate of the universe. Over the past century, our understanding of the universe has come a long way, thanks to groundbreaking discoveries like inflation theory and dark energy, as well as the work of Space Telescope inventor Hubble. At the boundary of our observable universe lies the cosmic horizon, the farthest point from which light has traveled to reach Earth. This distance has been measured from the beginning of the universe, which is approximately 138 billion years ago, and the light from everything beyond the cosmic horizon is currently unobservable because its light hasn't had enough time to reach us. This doesn't imply that nothing exists beyond the horizon. It simply means that we can't see it yet. The idea of redshift is crucial in this regard. The most distant objects we can see have been traveling for 138 billion years, but due to the expansion of the universe, they are now much farther away than that. The cosmic horizon explains that distant galaxies appear redshifted in our telescopes. This means that their light waves have been stretched to longer wavelengths, or towards the red end of the spectrum, as they recede from Earth. The faster a galaxy is receding, the larger its redshift, so we can measure its distance and speed to piece together its expansion history. When we observe faraway galaxies, it's as if we're peering into a time capsule. Light travels at a constant rate across space, so what we see now isn't always reflective of the actual state of the universe. For instance, when we look at a galaxy that's 10 billion light-years away, we see it as it was 10 billion years ago. This allows us to learn about the universe's evolution over billions of years, but it's only a small fraction of the total. Beyond the cosmic horizon is the unobservable, the vast expanse of space. Areas of the cosmos that aren't visible to the naked eye because their light hasn't yet reached ours. The difference between the two, known as the observable and unobservable universes, is important for a number of reasons, the most important of which is that it influences our conception of the size and structure of the universe. While the observable universe is enormous, it represents a small fraction of the entire, potentially infinite, universe. This implies that there may be innumerable galaxies, stars, planets, and regions outside of our field of vision, as well as areas with distinct physical laws or properties. The observable universe provides clues about the overall shape and topology of the universe. Scientists estimate what lies beyond the horizon based on models and observations from the observable universe. These models help us understand if the universe is flat, open, or closed, and how it could change in the future. Lastly, there are philosophical implications of the distinction between the observable and unobservable universes. It challenges our perception of reality and our place in the cosmos, knowing that there are regions of the universe that we will never see, regardless of how much we try. Scientists can learn about the conditions and processes that occurred shortly after the Big Bang by studying the light from the most distant galaxies. This light comes from a time when the universe was very young. By studying this light, we can refine our models of cosmic evolution and the formation of the cosmos. The limits of human knowledge and the vastness of the cosmos are both brought to light by the increasing sophistication of our technology. The study of galaxies and large-scale structures, the cosmic horizon, and the observable universe is interconnected with many other branches of cosmology and astrophysics. For instance, it is related to the study of the mystery components of the universe, dark matter and dark energy, which comprise the vast majority of its mass and energy. Gaining insight into how these components impact the expansion and structure of the cosmos allows us to construct a more comprehensive picture of the cosmos. Lastly, there are philosophical considerations surrounding the concept of an infinite universe and the philosophical implications of the idea of. For ages, the concept of infinity has captivated people around the world. In cosmology, it represents the infinite nature of the universe, which defies human comprehension because our everyday encounters are confined to finite spaces and objects. On the other hand, in mathematics, infinity is more than just a theoretical concept. It is a concrete idea with real-world applications. Mathematicians have developed a rigorous framework for working with infinite quantities. For example, calculus deals extensively with infinite series and limits, allowing us to approach the infinitely small and the infinitely large in a structured manner. Infinity in mathematics helps us grasp the ungraspable by providing tools to analyze and describe phenomena that seem beyond our finite comprehension. When we think about an infinite universe, it poses profound existential questions. In an endless universe, where space goes on forever, the concept of a center or special location loses all meaning. Instead of seeing Earth and, by extension, ourselves as the center of the universe, we are reduced to a tiny dot in an enormous, possibly unfathomable expanse. This realization can be both humbling and unsettling. It challenges our sense of individuality. This idea, which is often explored in science fiction, suggests a multiverse where every possible outcome exists somewhere. It is speculative, but it invites us to ponder the limits of reality and our perception of it. Could there be countless versions of our world? Additionally, the concept of an infinite universe brings into question the nature of existence itself. There are two main interpretations of the anthropic principle, the weak and the strong. The weak one states that the observed values of physical constants in the universe must be compatible with the conscious life that observes them. This leads us to consider alternate realities, each slightly different from the one we know. If this is the case, what does it mean for our understanding of identity and individuality? These considerations bring us to the anthropic principle, a philosophical idea. The strong anthropic principle believes that the universe must have properties that inevitably lead to the development of conscious life. This suggests that the universe was somehow designed with the emergence of observers in mind, rather than being completely random. If these constants were even slightly different, life, as we know it, would not be possible, and we wouldn't be here to observe them. This interpretation raises profound questions about the nature of reality. Given the boundless variety of possible locations throughout the universe, it stands to reason that some of these spots will have the ideal circumstances for life to flourish. Fortunately, we happen to be located in one of these spots, thanks to the anthropic principle, which offers a framework for comprehending the universe's current state despite its apparent fine-tuning. Areas not because they're exceptional or rare, but because they're among the few places where observers like us could live. Nevertheless, the anthropic principle isn't without its detractors. Some say it's just a statement that has to be true but doesn't explain anything, while others say it suggests teleological explanations in the structure of the universe, suggesting purpose or design. Regardless of these concerns, the anthropic principle is still a useful tool for investigating the philosophical ramifications of our existence in a bizarre. An endless universe begs the philosophical question: what is reality? If the universe is infinite, then every conceivable event, no matter how remote, must occur at some point. This begs the question, in a deterministic universe, where every event is the product of those that came before it, controlled by the laws of physics, is free will really real, or are we just blindly following one of these theories? Infinitely many possible outcomes, the cosmos's limitless size compels us to reevaluate our conception of time. If space is limitless, then perhaps time is as well. The idea of an eternal universe calls into question our traditional view of time as a discrete continuum, wherein events occur in discrete moments with discrete beginnings and endings. This idea of an endless universe adds another dimension to the philosophical investigation of infinity. It raises the question of whether our individual lives have any inherent purpose or meaning in the vast and interconnected web of existence. Some may find this prospect frightening, believing that our place in it is insignificant compared to the rest of creation. On the other hand, others may find solace in the idea that we are part of something much bigger, reflecting the larger human experience. The importance of interdisciplinary approaches to understanding the cosmos is underscored by the intersection of science and philosophy. In this experience, where we are constantly seeking meaning in a world that often seems indifferent to our existence, we must also consider the role of science in addressing these profound questions. Science provides us with tools to explore and understand the universe, but it also has its limits. While we can develop theories and models to describe the infinite, our finite minds and tools can only grasp so much. By integrating scientific research with philosophical contemplation, we can develop a more sophisticated comprehension of our role in the vast cosmos. In the end, the idea of an endless universe compels us to embrace the mystery of multiverse theories. When we explore these theories, we delve into some of the most fascinating and intricate concepts in contemporary physics. These theories propose that our universe could not be unique, but rather one of innumerable others, each with its own set of characteristics and physical laws. At its core, string theory proposes that the fundamental building blocks of a universe are not particles, but tiny vibrating strings of energy. These strings can vibrate at different frequencies, and the properties of particles are determined by their vibrations. String theory aims to unify all the fundamental forces of reality, expanding our understanding of reality beyond what we can observe and measure. Natural phenomena, including gravity, into a unified theoretical framework. One intriguing feature of string theory is that it mandates more than the familiar three dimensions of space. In fact, it has been proposed that there could be as many as 10 or 11 dimensions. Typically, these additional dimensions are believed to be compacted or curled up to a point where they are imperceptible. However, in certain variants of string theory, these additional dimensions could result in the existence of parallel universes, each with its own unique set of physical laws, properties, and they may exist independently of our own. The mathematical structure of string theory gives rise to the concept of parallel universes, which suggests that our own universe is just one among many. Each of these parallel universes may have its own distinct set of physical laws, and they may be incredibly diverse in terms of matter, energy, and even dimensions. The concept of parallel universes is both intriguing and challenging because it forces us to think beyond our current understanding of reality. Bubble universes, the idea behind which originates from the theory of cosmic inflation, postulates that the early cosmos expanded at an exponential rate in the first few moments of our universe's existence. If this theory is correct, then different parts of space could have ceased expanding at different points in time, resulting in the formation of unique bubbles of space-time. These bubbles would presumably not interact with one another, but rather exist independently of one another. Separate areas of space, potentially separated by vast distances or even dimensions. The notion of bubble universes suggests that there may be an infinite number of other universes, each with its own distinct properties. Some of these universes may be very similar to ours, while others may be completely different, containing completely different types of matter and energy. By understanding the structure of the multiverse, we can better comprehend the possibility that our universe is merely one bubble in a vast cosmic foam with other. Quantum mechanics, the branch of physics concerned with the behavior of subatomic particles, is famous for its illogical and frequently bizarre predictions. One of its basic principles is that particles can exist in multiple states. This idea is constantly evolving and expanding our knowledge of the universe, and it challenges us to think beyond the boundaries of our observable universe. Another intriguing theory is multiverse theory. Superposition, according to the many worlds theory, happens whenever a quantum event takes place, splitting the universe into numerous parallel worlds, each of which represents a different outcome of the quantum event. For instance, if a particle can exist in two places at once, the universe splits into two parallel worlds, one where the particle is in one place and another where it is in the other. This process of splitting happens constantly, creating an infinite number of parallel worlds in the cosmos. The concept of many worlds poses intriguing questions about the nature of existence and challenges our understanding of reality. According to this interpretation, every possible outcome of an event exists in its own parallel world. This implies that there are countless versions of reality, each with its own subtle differences. Some of these parallel worlds could be quite similar to our own, while others could be completely different. It's baffling because it implies that the universe is always splitting into multiple versions of reality, each with its own set of facts. This idea challenges our sense of time and causality because it means that every conceivable future exists in separate worlds. Theories like the multiverse, string theory, parallel universes, bubble universes, cosmic inflation, and many worlds' interpretation of quantum mechanics all point to the possibility that our universe is just one of many. These theories not only broaden our comprehension of the universe, but also encourage us to contemplate the deep implications of a multiverse. If numerous universes exist, each with its distinct characteristics, what does this imply for our comprehension of reality? The concept of a multiverse poses deep philosophical questions regarding reality, our position in the universe, and the basic laws that govern existence. How can we make sense of our everyday lives in light of the possibility of parallel universes? These questions push us to ponder the fundamental questions about our place in the universe and the boundaries of our understanding. The investigation of multiverse theories showcases our insatiable appetite for knowledge and our eagerness to seek answers to these profound questions. Black holes and their implications are two of the most enigmatic and fascinating topics in this regard. Cosmic objects, regions of space where the force of gravity is so great that not even light can escape them. The boundary surrounding a black hole, beyond which nothing can be recovered, is known as the event horizon. Once an object crosses this boundary, it is bound to be pulled into the black hole. The event horizon is symbolic of both the physical and philosophical boundaries of our knowledge of what happens inside a black hole. When a black hole, mainly due to his theory of Hawking radiation, crosses the event horizon, it is permanently hidden from our view. This poses a challenge to our perception of reality since it implies that there are areas of the universe that are essentially inaccessible to us. The very existence of event horizons compels us to face the limits of human knowledge and the boundaries of what we can observe and comprehend. Black holes were previously believed to be totally opaque, with no means of evading their gravitational pull. However, Hawking demonstrated that, as a result of quantum effects close to their event horizon, these objects could emit radiation. This radiation, now referred to as Hawking radiation, is the product of the black hole's interaction with the quantum vacuum. Hawking radiation has significant implications for our knowledge of black holes, as it implies that these objects are not totally opaque and can actually lose mass and energy. Long-term exposure to Hawking radiation has the potential to cause a black hole to completely dissipate, casting doubt on the long-held belief that these objects exist in a static state. Instead, it could indicate that black holes are dynamic, ever-changing entities that interact with their environment in fascinating ways. One of the most intriguing mysteries surrounding black holes is the information paradox, which is defined as the full description of a physical system's state according to the principles of. Information should always be preserved, even when transformed or hidden, according to quantum mechanics. However, black holes present a paradox. When an object falls into one, all knowledge about its state appears to be lost. What's more, if the black hole eventually evaporates due to Hawking radiation, it would appear as though the information is permanently lost, violating the principle of information preservation. The information paradox has sparked heated discussion and investigation among physicists, with no clear consensus on a solution. One theory holds that the information is encoded in the Hawking radiation, which is still under investigation. Another theory suggests that the information is stored on a holographic surface surrounding the black hole, a concept called the resolution of the information paradox could lead to significant advances in our understanding of quantum mechanics and the nature of the universe. Black holes also raise important questions about the nature of space and time near the event horizon, where the effects of gravity are so extreme. The holographic principle, the information paradox, and other aspects of black holes present significant challenges to our current understanding of the universe. The extreme conditions near black holes provide a unique laboratory for testing the laws of physics. They offer insights into the behavior of matter and energy under the most extreme conditions and challenge our understanding of the universe. As an object approaches the event horizon, time appears to slow down and eventually come to a complete stop at the horizon itself. This means that an observer falling into a black hole would experience time very differently from an outside observer. The very fabric of reality, studying black holes allows us to test the boundaries of our understanding and discover what's next in modern physics. However, beyond the event horizon, there's a point called the singularity, where the force of gravity is infinite and space-time curvature is infinite as well. At this point, our present understanding of physics breaks down, as the laws of general relativity, which normally govern how gravity behaves, no longer hold under these extremely harsh conditions. The existence of the singularity highlights the gaps in our present theories of gravity and the necessity for a more thorough and updated framework. A primary objective of contemporary physics is the development of a theory that can account for the peculiarities of gravity at the singularity. This proposed theory, sometimes called quantum gravity, would bring together the fundamental ideas of general relativity and quantum mechanics, outline in detail how matter and energy behave under the most extreme circumstances, and perhaps provide some novel insights. Black hole research has already led to substantial advances in our knowledge of the cosmos, the discovery of phenomena that defy our traditional view of reality, and the opening of new research avenues. As we delve deeper into the mysteries of black holes, we can expect to find out even more surprising things about the universe and our role in it. Black holes also affect our perception of. The study of black holes brings up important questions about the future of the universe and their role in cosmology and its evolution. Supermassive black holes, which are hundreds of thousands of times heavier than the Sun, are located at the heart of the vast majority of galaxies, including our own Milky Way. These black holes impact the formation and evolution of the galaxies they inhabit. Can dissipate via Hawking radiation. What does this portend for the cosmos's long-term development? Will all black holes eventually dissipate, leaving behind an empty universe teeming with elementary particles? These questions test our grasp of the universe's ultimate destiny and the very nature of time. The investigation of black holes and their mysteries is an embodiment of the strength of human curiosity and the desire to comprehend the cosmos. It shows that we are prepared to face. As we delve into the study of black holes, we are not only seeking answers to specific scientific questions, but also exploring the deeper philosophical implications of our existence. This discipline compels us to confront the limits of our knowledge and seeks answers to some of the most profound questions about the nature of reality. By doing so, we are constantly expanding our understanding of the cosmos and the unknown. As we ponder the essence of reality, we are compelled to delve into profound questions regarding space-time and information, as well as the universe's fundamental mysteries. By studying black holes, we can better understand and appreciate these enigmatic phenomena. The search for a unifying theory, sometimes called a theory of everything, is among the most audacious and profound endeavors in contemporary physics. This pursuit seeks to reconcile two of the most influential frameworks in 20th century physics, general relativity and quantum mechanics, respectively, seek to explain the behavior of forces and particles at the atomic and subatomic levels, while general relativity explains the structure of space and time at the largest scales and the force of gravity. They are fundamentally incompatible with each other, but a unified theory aims to bridge this gap. Subatomic levels. It lays out a universe where particles can be in different states at the same time, entangled over long distances, and where outcomes are determined by probability. This theory has generated a lot of technical progress, from semiconductors to magnetic resonance imaging, MRI machines. However, when it comes to the gravitational field, quantum mechanics has a hard time explaining how gravity behaves. This is in contrast to general relativity, which Albert Einstein proposed and which changed the way we see the world. This theory explains gravity as a curvature of space-time brought about by mass and energy. It successfully predicts planetary motion, the bending of light due to gravity, and the dynamics of the universe at large scales. However, it fails to account for the principles of quantum mechanics, which control the microscopic realm. Consequently, when applied to situations where both quantum effects and strong gravitational fields are significant, like inside black holes, the two theories yield contradictory predictions, or came to light as a potential unifying theory during the Big Bang. String theory posits that the building blocks of the universe are not point-like particles, but rather small vibrating strings, the frequencies of which correspond to different particles. This theory incorporates gravity by definition and has the ability to reconcile it with quantum mechanics by viewing particles as one-dimensional objects instead of zero-dimensional points. Helps resolve many inconsistencies and infinitesimals that occur when the two frameworks are combined. String theory also adds dimensions beyond the usual three. Sometimes these dimensions are compactified, meaning they are so twisted that they aren't visible at ordinary scales. Theoretically, string theory suggests that there could be as many as 10 or 11 dimensions. These hidden dimensions offer a framework for bringing everything together. Fundamental forces, such as gravity, electromagnetism, and the strong and weak nuclear forces, M-theory, an expansion of string theory, integrates the 5 distinct formulations of string theory into a unified framework. It proposes that the universe's fundamental objects are not merely strings, but rather higher-dimensional membranes or branes, each of which can possess multiple dimensions. In our universe, as one such three-dimensional brane floating in a higher-dimensional space, could be an example of this, and is looked upon as a frontrunner for a theory of everything, despite the fact that string theory and M-theory encounter considerable obstacles. The primary problem is that these theories are hard to test experimentally because the scales at which string effects become noticeable are so tiny and the energies needed to investigate them are so high, surpassing the capabilities of present technology. Furthermore, string theory foretells a wide array of potential solutions that correspond to various universes that could exist, each with its own unique set of physical characteristics, making it difficult to determine which, if any, of these solutions applies to our own. One competing theory that aims to bring quantum mechanics and general relativity into harmony is loop quantum gravity. Rather than viewing gravity as a constant force acting against a fixed background in space-time, loop quantum gravity proposes that space-time is actually composed of discrete quantized loops at scales on the order of the Planck length, which is approximately 10 circumflex 35 m. The smooth fabric of space-time breaks down into a network of finite loops. Loop quantum gravity takes into account the quantization methods of quantum mechanics, while attempting to maintain the principles of general relativity. A significant accomplishment of this theory is the derivation of a discrete structure of space, where space is made up of finite loops or quanta space. This discrete nature has the potential to address the This theory proposes that the singularities predicted by general relativity are actually finite quantized structures, which could explain the Big Bang instead of the beginning of time. Instead, it suggests that the Big Bang was a transition from a previous contracting phase to our current expanding phase, a concept known as the infinity problem in quantum gravity. Another important contribution of loop quantum gravity is its potential explanation for the Big Bang. Loop quantum gravity and string theory offer complementary but distinct ways of looking at the universe's basic nature. String theory aims to bring all fundamental forces together through vibrations in strings and higher-dimensional branes, while Big Bounce suggests a cyclic model of the cosmos, where each cycle starts with a bounce instead of a singularity. This viewpoint offers a fresh take on the universe's beginnings and evolution. Both theories shed light on the quantization of space-time, but they also present formidable obstacles. Perhaps the ultimate theory will combine aspects of both approaches. Seeking a unifying theory is more than simply a quest for a formula that can explain everything in the universe. It's also an adventure into discovering the fundamental laws that control it, forcing us to reconsider our long-held beliefs about space-time and matter and delving into the mysteries of the cosmos. The eternal quest for a unifying theory pushes the limits of our understanding, compels us to think beyond the confines of our present comprehension, and ultimately, it beckons us to delve into the enigmas of the universe. As we delve deeper into these theories, we are reminded of the immense power of human curiosity and the urge to comprehend the universe as a whole. Gazing up at the universe with awe and curiosity, we are constantly exploring new theories in our never-ending quest to understand it all. Whether it's the complex mathematics of string theory, the discrete structures of loop quantum gravity, or some other framework that hasn't been found yet, we're always learning and growing in our pursuit of a unified theory. This pursuit represents the pinnacle of human intellectual achievement and is a testament to our enduring quest too. When we examine the cosmos on a large scale, we observe a beautiful tapestry of cosmic structures, galaxies, clusters, and superclusters that form a complex web. This reminds us that the quest for knowledge is an ongoing journey that demands creativity, perseverance, and a willingness to embrace the unknown. String theory, quantum gravity, and other approaches help us understand the universe and our place within it. Universe galaxies are the building blocks of our universe, each housing billions of stars, planets, and other celestial bodies held together by gravity. Our Milky Way galaxy is one such massive system, gracefully spiraling through space. Galaxies do not exist in isolation, but rather in clusters with hundreds or thousands of galaxies orbiting a common center of mass. Stellar events like galaxy collisions and star formation are common outcomes of galaxy cluster interaction. Even more massive than clusters are superclusters, which are massive assemblies of galaxy clusters. These structures are among the biggest known in the universe, spanning hundreds of millions of light years. Superclusters resemble a cosmic web, with filaments of galaxies and clusters linked by large gaps in space. Despite their names, the vast majority of the universe is composed of two concepts: dark matter and dark energy. Despite not emitting, absorbing, or reflecting light, we can infer their presence through their gravitational influence on radiation from visible matter and the expansion of the cosmos over billions of years. One of the most fascinating aspects of the universe's large-scale structure is that much of it is invisible to us. Massive cosmos dark matter is thought to comprise around 27% of the total mass and energy of the universe. It doesn't interact with electromagnetic forces, so it doesn't give off any visible light or energy that our instruments can detect. However, its gravitational pull causes galaxies and clusters of galaxies to spin faster than what can be explained by visible matter alone. This invisible framework helps explain the distribution and movement of galaxies and clusters we see today. Dark energy, which is even more mysterious, is believed to comprise approximately 68% of the universe and is responsible for its expansion and contraction. Dark matter is believed to act as a scaffolding for the universe, clumping together under the influence of gravity to create the conditions necessary for galaxy formation. The standard model of Big Bang cosmology is the Lambda CDM model, which refers to the expansion of the universe at an accelerated rate. This expansion was initially noticed in the late 20th century when astronomers found that distant galaxies were receding from Earth at a faster rate than predicted. Dark energy, which acts as a repulsive force counteracting gravity, is responsible for this expansion. Despite its profound effects on the cosmos, the nature of dark energy is one of the biggest mysteries in cosmology. According to the Lambda CDM model, the universe started with the Big Bang, a rapid expansion from an extremely hot and dense state about 138 billion years ago. Cold dark matter, CDM, is a subset of dark energy in Einstein's field equations of general relativity. The model provides a comprehensive framework for understanding the evolution and structure of the universe from its earliest moments to the present day. The Lambda CDM model explains the observed large-scale structure of the universe, the cosmic microwave background radiation, and the abundance of light elements such as hydrogen and helium. It also accounts for the accelerated expansion of the universe due to dark energy and provides a framework for understanding how dark matter influences the formation and evolution of cosmic microwave background radiation, atoms, stars, and galaxies. Studying the large-scale structure of the universe and the role of dark matter and dark energy requires sophisticated tools and techniques. Observations from ground-based telescopes, space-based observatories, and cosmic microwave background experiments. Discrepancies exist between the model's predictions and certain observations, such as the rate of cosmic expansion, and the model's exact nature of these substances is still unknown. We can learn more about the universe and its early stages by studying the cosmic microwave background, CMB, radiation, which is a faint radiation that fills the cosmos and provides a snapshot of the universe when it was only 380,000 years old. This radiation helps scientists map the distribution of galaxies, measure the effects of dark matter and dark energy, and test the predictions of the Lambda CDM model. The conditions of the cosmos and the distribution of matter and energy. Precise measurements of the cosmic microwave background, CMB, taken by missions like the Planck satellite have strongly supported the Lambda CDM model. Another significant field of study is that of galaxy clusters. These enormous structures are affected by dark matter and dark energy, making them useful probes of the universe's makeup and evolution. Observations of galaxy clusters, including their distribution, motion, and interaction with the one of the most effective ways that scientists have found to study dark matter is gravitational lensing. This phenomenon occurs when light from a faraway galaxy bends as it approaches a massive object, such as a galaxy cluster. As a result, scientists are able to create distorted or multiple images of the background galaxy, which they can then analyze to determine the distribution of dark matter in the universe. Future missions like the James Webb Space Telescope and the European Space Agency's Euclid mission promise to offer even more detailed observations of the universe, revealing its most basic mysteries. The study of large-scale cosmic structures, dark matter, and dark energy is a rapidly evolving field, with new discoveries and technological advancements constantly pushing the boundaries of our understanding. The Lambda CDM model offers a strong framework for understanding the evolution of the universe because it incorporates dark matter and dark energy, which are invisible components of the cosmos. Our quest to understand these cosmic mysteries drives us to develop new technologies, refine our theories, and expand our knowledge. Through our efforts, we have shaped the universe we see today, impacting everything from galaxy formation to the expansion of the universe itself. Exploring cosmic structures and the roles of dark matter and dark energy is a testament to human curiosity and the drive to understand the universe. It challenges us to delve deeper into their nature and emphasizes the importance of these unseen components in shaping the cosmos. As we continue to study the cosmos, we are likely to uncover new insights and refine our models, bringing us closer to a more complete understanding of the cosmos, more enigmatic than we could have anticipated. Through research into these cornerstones of the universe, we uncover not only its history and present, but also its potential future and our own position within it. One of the most fascinating and hotly contested topics in contemporary science and philosophy is the function of observers. According to the participatory anthropic principle, observers are not merely passive entities in the universe, but rather play an essential role in shaping it. Building on the anthropic principle, which states that the universe must be compatible with the conscious beings that observe it, the participatory version goes further, suggesting that the universe requires observers to bring it into being. This idea was extensively promoted and challenges the traditional view of the universe as a detached, objective reality. Instead, it proposes that the act of observation is fundamental to the existence and nature of the universe. The idea was put forth by physicist John Arkell Wheeler, who argued that the act of observation could change reality itself. According to Wheeler, the universe doesn't exist until someone looks at it, and observers have a significant impact on the universe's shape. This principle suggests that the presence of observers is crucial for the universe to display its properties. Without them, the potential states of the universe would remain unfulfilled. Wheeler's concept challenges our current understanding of existence and suggests a fascinating and perplexing aspect of quantum mechanics is the role of observation in determining the state of a quantum system. In this realm, particles can exist in a state of superposition, meaning they could be in multiple states at once. However, when an observation or measurement is taken, the state of the system is changed. This further deepens our understanding of the relationship between observers and the universe. The classic example of this phenomenon, known as wave function collapse, is the double-slit experiment. In this setup, particles like electrons are shot at a barrier with two slits. When no one is looking, the particles behave like waves, creating an interference pattern on a screen behind the barrier. However, as soon as someone is measuring which slit the particles pass through, the interference pattern disappears. This experiment shows that superposition collapses into a single definite state. The classical view of an objective, observer-independent reality is challenged by the idea that the act of observation fundamentally alters the behavior of quantum systems. This idea has profound implications for our understanding of reality, as it suggests that the quantum level of the universe is not deterministic, but is influenced by the presence of observers. Thus, consciousness plays a critical role in shaping the universe. The relationship between consciousness and the cosmos is a matter of heated controversy. On one hand, there are many who believe that consciousness is as essential to the cosmos as matter and energy. This would mean that consciousness is not just a result of complicated physical processes, but an inherent part of reality. On the other hand, there are many who believe that the relationship between consciousness and the cosmos is too intricate to be completely understood using conventional scientific methods. There are certain ways of looking at quantum mechanics that put the onus of proof squarely on the observer. If consciousness is key to the cosmos, then maybe the cosmos is conscious or at least permeates all levels of reality. On the other hand, maybe the universe is designed to foster consciousness. In this view, the physical constants and laws of nature seem to be fine-tuned to support life, and thus consciousness. This fine-tuning has prompted some to wonder if consciousness is a built-in feature of the universe, implying a closer bond between the cosmos and the conscious beings who live in it. Exploring this link makes us think about what awareness is all about. Consciousness is often seen as an enigmatic and elusive phenomenon, one that doesn't lend itself to simple explanations. By delving into its relationship with the cosmos, we can potentially uncover new insights, delves into the nature of consciousness and the workings of the universe. The participatory anthropic principle, quantum mechanics, and the study of consciousness all point to a profound connection between observers and the universe. These ideas make us question our current reality and ask us to reevaluate our very existence. They imply that the universe is not an immutable, objective entity, but rather profoundly affected by conscious beings. This interconnectedness invites us to explore the universe as active participants in the unfolding of reality, rather than passive observers. The role of observers in the universe takes us on a journey into the heart of some of the most profound questions about existence, challenging us to consider the nature of reality and the influence of consciousness. As we delve into the study of quantum mechanics and consciousness, we are invited to broaden our horizons, explore the depths of reality, embrace the unknown, and consider the possibility that the universe is far more interconnected and dynamic than we ever imagined. We gain a deeper appreciation for the intricate and mysterious ways in which the universe and consciousness are interwoven through this exploration. Here on Quest, we are reminded of how powerful our curiosity can be and how much we want to know about the universe. The role of observers in the cosmos shows how much of an influence consciousness has on reality, and it invites us to investigate the basic principles that determine our existence. If we keep studying these concepts, we might find new insights and a better grasp of our place in the universe. One of the most fascinating and confusing phenomena in quantum mechanics is the observer effect, which is music. Quantum mechanics describes the behavior of particles at the smallest scales, where the principles of classical physics no longer apply. At its core, the observer effect challenges our classical understanding of reality by suggesting that the act of observation can alter the state of a quantum system. At its core, the observer effect highlights the intimate relationship between measurement and observation and the nature of reality. When an experiment is conducted, particles like electrons or photons are fired at a double slit, which is a classic example of the observer effect. In this experiment, particles are observed to be in a superposed state, meaning they could be in two different locations or have multiple possible energies all at once. This phenomenon is called wave function collapse. The double slit experiment involves a barrier with two slits. When no one is looking, the particles behave like waves, creating an interference pattern on the screen behind the barrier. This pattern shows that each particle passes through both slits at the same time, interfering with itself. On the other hand, when someone is measuring which slit the particles pass through, the interference pattern disappears, and two separate bands appear on the screen, one for each slit. Shows how seeing something changes the way quantum systems work. When particles aren't observed, they act like waves in a state of superposition, but when they are, their positions and trajectories become crystal clear. This phenomenon makes us wonder what reality is and how consciousness fits into the cosmos. One way to look at this phenomenon is through the Copenhagen interpretation of quantum mechanics, which was developed by Niels Bohr and the Copenhagen interpretation, put forth by Vera Heisenberg in the early 1900s, holds that, at the quantum level, reality is intrinsically probabilistic, and that observation is pivotal in determining the properties of a quantum system. This interpretation states that a quantum system exists in a superposition of states until it is measured, at which point it is forced to choose one of its possible states, resulting in the collapse of the wave function into a single outcome. According to Hugh Everett's 1957 Many-Worlds interpretation of the observer effect, every possible outcome of a quantum event actually occurs, but in separate, discrete worlds. This theory challenges the classical view of an objective reality that exists independently of our observations, and instead proposes that the act of observation is an integral part of the process influencing the state of the system being observed. According to the Many-Worlds interpretation, all potential outcomes in quantum mechanics exist simultaneously in a vast multiverse. This theory proposes that when a measurement is made, the universe splits into multiple branches, each of which corresponds to a different outcome. Rather than collapsing the wave function, the observer effect creates multiple parallel realities. There is a continuous debate and investigation into the role of consciousness in the observer effect. Some interpretations propose that consciousness itself is fundamentally involved in collapsing the wave function. This idea is often linked to the work of physicist Eugene Wigner and raises profound questions about the nature of reality and our place within it. It challenges our conventional understanding of existence and the existence of parallel universes, each with its own version of reality. Another school of thought contends that the observer's mental state is pivotal to the final result of a quantum experiment. If this is so, then consciousness is not a mere observer, but rather an integral part of the process that gives rise to reality. This view runs counter to the conventional wisdom in science, which holds that consciousness is nothing more than an effect of physical laws. A number of philosophical and speculative ideas have arisen in relation to the relationship between consciousness and the observer effect. One such principle, advocated by physicist John Archal Wheeler, states that the act of observation is crucial for the collapse of the wave function and proposes that consciousness directly affects the very fabric of reality. According to this theory, the cosmos is not a static backdrop, but rather an interactive, participatory reality that relies on the presence of conscious observers. This idea challenges our current conception of reality and prompts us to contemplate the prospect that, in a quantum computer, for instance, a qubit, a quantum bit, can exist in multiple states at once, enabling for parallel processing of information. However, when a qubit is measured, its superposition collapses, implying that consciousness plays a fundamental role in constructing the cosmos, and the observer effect has practical implications for the advancement of quantum technologies. Due to the fact that the act of observing the quantum states used to encode information introduces disturbances that can be detected by the legitimate parties, it becomes challenging to extract information without disrupting the computation in quantum cryptography. In quantum key distribution protocols, such as the BB84 protocol, the principles of quantum mechanics are used to create secure communication channels. The observer effect provides a basis for the security of quantum communication by altering states to reveal the presence of an eavesdropper. This has important implications for the development of secure communication networks and the protection of sensitive information. Beyond its practical applications, the observer effect invites us to explore deeper philosophical questions about reality and the role of. Recent developments in cosmology have greatly enhanced our comprehension of the cosmos, thanks to instruments like ground-based and space telescopes, as well as new ideas like consciousness, which challenge the traditional idea of an impartial observer-free universe and propose that observation is fundamental to the creation of reality. This new way of thinking encourages us to contemplate the idea that reality is not static and unchanging, but rather intricately connected to the existence of conscious beings. Astronomers have made remarkable discoveries thanks to space-based instruments that have allowed us to peer deeper into space and time. The instruments have grown increasingly powerful and sophisticated over the years, allowing astronomers to use them to observe the universe. The earliest telescopes, constructed in the early 17th century, utilized simple lenses to magnify the light from faraway objects. This allowed astronomers like Galileo to make significant strides in the field. The 18th century, reflecting telescopes that utilized mirrors instead of lenses, enabled even greater magnification and clarity. In the 20th century, a new window onto the cosmos was unveiled by the development of radio telescopes, which detected radio waves emitted by celestial objects, providing information that is not visible in optical light. This technology led to the discovery of. Through their ability to bypass Earth's atmosphere, which can distort and block certain wavelengths of light, space telescopes have greatly improved our ability to observe celestial objects. By positioning themselves above the atmosphere, space telescopes like the Hubble Space Telescope offer a clear and unobstructed view of the cosmos, allowing us to study phenomena like pulses, K-Earths, and the cosmic microwave background radiation, which is the afterglow of the Big Bang. The Hubble Space Telescope, one of the most monumental space missions of all time, was launched in 1990 and has since transformed our understanding of the cosmos. It has allowed us to measure the expansion rate of the universe, discovered dark energy, and improved our understanding of star formation and star life cycles. Countless scientific papers have been authored as a result of Hubble's observations. JWST, the James Webb Space Telescope, is set to launch in December 2021 and is part of the next generation of space observatories. It will be able to study the formation of stars and planets by observing the universe in the infrared spectrum, which will allow it to see through dust clouds. JWST's powerful instruments will also allow it to look back in time to the first galaxies that formed after the Big Bang, providing insights into the early universe. JWST's advanced technology and, with its larger mirror, it will become one of the most powerful telescopes ever constructed, capable of making discoveries that were previously unimaginable. Other notable space missions have also added to our knowledge of the cosmos. The 2009 launch Planck satellite mapped the cosmic microwave background radiation with unprecedented precision, revealing details about the early universe and the basic parameters of cosmology. The 2009 launched Kepler Space Telescope found thousands of exoplanets. Increasing our understanding of planetary systems beyond our own is a promising goal for future space missions and observatories. The UID mission, set to launch in 2022 by the European Space Agency, will study dark matter and dark energy with high precision, survey billions of galaxies across a large portion of the sky, and provide critical data to test cosmological models and theories. Another important survey is the Large Synoptic Survey. Another exciting project is the Square Kilometre Array, SK, the largest next-generation radio telescope, which is set to begin full operations in the early 2020s. The Vera C. Rubin Observatory, formerly known as the Telescope LSST, will undertake a 10-year sky survey, snapping detailed images of billions of objects. Its deep imaging capabilities and wide field of view will enable it to study everything from asteroids in our solar system to distant galaxies and dark energy. SKA, the largest and most sensitive observatory of its type, will be constructed in 2 stages, with sites in South Africa and Australia. When finished, it will have a total collecting area of more than 1 square kilometer, enabling it to detect faint radio signals from the early universe. SKA will tackle numerous scientific inquiries, including how stars and galaxies formed, the composition of dark matter, and the source of dark energy. Technological advancements are also improving the capabilities of ground-based telescopes, such as the extraordinarily large telescope. The ELT, a massive optical and infrared telescope now under construction in Chile, will have a primary mirror 39 meters in diameter. With this innovative technology, astronomers will be able to study distant objects like black holes, exoplanets, and star formation with greater clarity than ever before. Adaptive optics is another technical advancement that has greatly enhanced the efficiency of ground-based telescopes. It compensates for, through the application of adaptive optics to numerous existing telescopes, we are able to see faint and distant objects with greater clarity, allowing us to achieve near-space-based image quality. The combination of these technological advancements is transforming our ability to explore and understand the universe. With each new telescope and observatory, we gain new tools and perspectives, which allows scientists to probe deeper into the mysteries of the cosmos. Progress in space exploration is constantly pushing the boundaries of what we know and what we can study. For example, in 2015, the New Horizons mission flew by Pluto, giving us our first up-close look at this faraway world and revealing its surprisingly complex and dynamic landscape. Since then, New Horizons has continued its journey into the Kuiper Belt, where it is exploring other faraway objects and illuminating the outer regions of our solar system. Another example is the Parker Solar Probe, which has been sending out images of our solar system and other far away. In 2018, NASA's Parker spacecraft set out on a historic mission to study the solar corona. By flying closer to the sun than any previous spacecraft, scientists are learning more about the processes that cause solar winds and space weather, which in turn affect Earth and our technological systems. The Mars rovers, which have explored the red planet's surface, have revolutionized our understanding of the red planet. In its 2021 landing, the Perseverance rover began analyzing Martian rocks and soil for evidence of past life. It also carried advanced instruments to study the Martian climate and geology, and it will gather samples to bring back to Earth. Missions like this one shed light on Mars's past and future habitability, opening the door to more human exploration. Europa Clipper, set to launch in the 2020s, will study Jupiter's moon Europa. Europa is thought to have an ocean beneath its icy surface. The mission will look for signs of life and determine if the moon is habitable. Dragonfly, scheduled to launch in 2027, will send a rotorcraft to Saturn's moon Titan. Titan is an intriguing target for exploration due to its diverse environment, thick atmosphere, and surface lakes of liquid methane and ethane. Researching the chemical makeup of prebiotics and the possibility of life in space is just the beginning of what cosmologists and space explorers are doing. It's not all about finding new stuff, though. They're also creating tools that can be used in other fields. For instance, adaptive optics technology developed for telescopes is finding new uses in medical imaging, where it's helping doctors diagnose and treat patients. The engineering and problem-solving skills needed for space missions are driving. Exploration of cosmological hypothetical scenarios and speculations raises some of the most fascinating and perplexing questions about our role in the universe. These ideas push the limits of our knowledge and challenge us to think beyond the known and observable. Some of these intriguing topics include the Fermi paradox, the simulation hypothesis, and given the immense number of stars and planets in our Milky Way galaxy alone, it appears statistically likely that intelligent life should have arisen elsewhere. However, despite our best efforts to detect signs of extraterrestrial life, we have yet to encounter any evidence of or contact with such civilizations. This paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" There are various theories put forth to explain the Fermi paradox. One is that intelligent civilizations are rare or have a short lifespan. Another is that societies with advanced technology develop infrequently. Lastly, civilizations could self-destruct before they can make contact with other societies due to wars, environmental degradation, or other self-inflicted problems. Another theory proposes that advanced societies may opt not to communicate with us. They might be watching us from a distance, either to let us evolve on our own or for ethical reasons not to interfere. This concept is sometimes called the zoo hypothesis, and it holds that Earth is being watched by advanced extraterrestrials like a cosmic zoo. It's also conceivable that we're not looking at the correct places at the right times. Philosopher Nick Bostrom put forth the simulation hypothesis, which is both a theory and a profound speculation about our reality. According to this theory, our universe could be an intergalactic simulation where aliens communicate using ways we don't fully comprehend or can't detect with our present technology. This notion underscores the limitations of our present search methods and the necessity for innovative approaches to discovering extraterrestrial life. Artificial simulation built by a highly advanced civilization. If this theory is correct, then it's statistically probable that we could be residing in one of these simulations. The simulation hypothesis, however, poses serious questions regarding the nature of reality and our role in it. After all, future civilizations with computing power far beyond our own could theoretically simulate entire universes with conscious beings inside. This idea raises philosophical questions about the purpose and meaning of life in a simulated reality, as well as challenges our understanding of existence and the fundamental nature of the universe. An approach to investigate the simulation hypothesis could be to search for anomalies or inconsistencies in the laws of physics that could indicate an artificial origin. Some scientists have even speculated that certain unexplained phenomena, like the nature of dark matter and the behavior of subatomic particles, could provide clues about the structure of a simulated universe. However, it is currently too difficult for us to understand and implement the necessary technology to confirm or refute this hypothesis. Another intriguing area of cosmology is the concept of alternate dimensions, which suggests the possibility of higher dimensions beyond the familiar three dimensions of space and time. One of the time is a cornerstone of theories like string theory, where extra dimensions are condensed or curled up to the point that they are not observable at everyday scales. If these higher dimensions do exist, they could influence the behavior of fundamental forces and particles in ways that we do not fully comprehend. For instance, gravity could be stronger or weaker in different dimensions, which could explain some theories propose the existence of parallel universes or branes in higher dimensional space, each with its own distinct properties and physical laws. These parallel universes could explain the anomalies in the behavior of galaxies and cosmic structures. There is also the possibility of alternate dimensions, which opens up intriguing theoretical scenarios. Higher dimensions could provide a framework for unifying the fundamental forces of nature, painting a more complete and coherent picture of the universe. The exploration of alternate dimensions is not merely a theoretical exercise. It has practical implications for our understanding of the UN universe. Experiments at particle accelerators, such as the Large Hadron Collider, LHC, are exploring the fundamental nature of matter and energy, searching for evidence of higher dimensions and other exotic phenomena. Such interactions occasionally cause observable effects, such as unexplained cosmic events or anomalies in the behavior of particles. The simulation hypothesis prompts us to ponder the essence of reality and our position within it. The Fermi paradox prompts us to contemplate the prospect of extraterrestrial life and the variables that could impact its detectability, and the exploration of alternate dimensions deepens our comprehension of space and time. These hypothetical scenarios and speculations push the boundaries of our knowledge and may unveil new insights into the fabric of reality. These ideas, which may appear far-fetched or speculative, actually represent the cutting edge of scientific thinking. They challenge us to expand our horizons and consider the deeper mysteries of existence with each new discovery and every passing moment, allowing us to better understand the universe and the role of imagination and creativity in scientific inquiry. The quest for knowledge continues with the development of new theories, which bring us closer to understanding the fundamental questions at the heart of cosmology. By delving into these ideas, our knowledge grows, and we're also inspired to think deeply about reality and the principles that govern the cosmos. The question of whether anything exists beyond the observable universe requires us to explore the boundaries of our current scientific understanding. The observable universe is defined by the cosmic horizon, which is beyond our sight due to the age of the universe and the finite speed of light. However, the very definition of the term suggests that there may be more to the universe than what we can see from a scientific perspective. The idea of the observable universe does not rule out the existence of regions beyond it. The observable universe is a spherical with a radius of approximately 465 billion light-years centered on Earth. The observable universe is thought to be a small fraction of the entire cosmos, according to the theory of cosmic inflation. This theory explains the uniformity of the cosmic microwave background radiation and the distribution of galaxies by proposing that regions beyond our observable universe undergo rapid expansion shortly after the Big Bang. On the other hand, the observer believes that the universe is much larger, possibly infinitesimally small. During inflation, the universe's regions grew closer together, but now they're too far away for us to see. If inflation is true, then there must be vast regions outside of our observable universe that contain galaxies, stars, and maybe even different physical laws, all driven by variations in the inflation field. Despite our limitations, these regions still exist according to the same physical principles that govern our own. Theories like string theory and the many worlds interpretation of quantum mechanics provide support for the multiverse hypothesis, which states that our observable universe is just one of many possible realities. According to this theory, other universes exist, each with its own unique set of physical constants and laws, which could explain why they seem completely different from our own. On the other hand, there is another version of the multiverse hypothesis that states that these other universes are causally disconnected from ours, meaning that we will never be able to interact with or observe them. Science is based on empirical evidence, But the existence of regions beyond our observational capabilities forces us to question what we can know and how we can know it. The idea of an unobservable universe makes us think about the limits of human knowledge and observation, which in turn raises deep philosophical questions about reality, knowledge, and existence. What does the existence of regions beyond the observable universe imply for our philosophical understanding of reality? It implies that reality encompasses more than just what we can perceive. It also includes a vast and possibly infinite expanse that we can speculate about, but never completely understand. This view is in line with the idea that human perception and cognition are. Dark energy and dark matter are fundamental concepts in cosmology. They're believed to play a driving role in the universe's accelerated expansion. And as the cosmos expands indefinitely, regions that are now visible will become invisible as they pass beyond our observable range. Given the ongoing expansion of the cosmos, the observable universe is expected to shrink in relation to the total size of the universe. This is because more regions will be beyond our observational reach, strengthening the idea that there are vast unobservable parts of the universe. However, technological and observational advancements could potentially expand the boundaries of the observable universe. For example, with more powerful ground-based and space-based telescopes, we could be able to see further and with greater clarity. Although there will always be a fundamental limit imposed by the speed of light and the age of the universe, theoretical models in cosmology are constantly improving and incorporating new data. These models imply that the universe is significantly larger than what we can see, which further supports the idea that the observable universe is merely a small part of a much larger, more expansive whole. Models such as the Lambda CDM, which incorporates dark matter and dark energy, offer a framework for the question of whether something exists beyond the observable universe touches on the very nature of cosmology and our quest to understand the cosmos scientifically. There is strong evidence to suggest that the universe extends far beyond what we can observe. Other theories, such as cosmic inflation and the multiverse hypothesis, provide plausible explanations for the existence of this vast and intricate cosmos beyond our observational limits. Exploring the regions beyond our observable universe is a testament to human curiosity and the drive to understand our place in the cosmos. It challenges us to consider the limits of human knowledge and the nature of reality, as well as the implications of existing in a vast and complex universe beyond our comprehension. Philosophically, the idea of an unobservable universe poses these questions. Look at or engage with these faraway places. The quest for information about them keeps scientists and philosophers thinking, which in turn increases our understanding and broadens our horizons. As technology advances and our theories are fine-tuned, we may eventually find the answers to some of the deep questions about the complexity and breadth of the universe. But until then, the unknown is a strong incentive to explore and discover, bringing to light the boundless potential that exists in the universe. If you found this video enjoyable, please consider leaving a like and subscribing. I appreciate you viewing.